So good morning, students. Yesterday you have seen about complex numbers, how a complex number can be represented geometrically. So today you people are going to see how USHASREE madam is going to tell you about the geometric conclusions of complex numbers and a few related problems regarding geometrical representation of a complex number. So over to USHASREE madam.
Thank you, madam. Good afternoon, everyone. Dear children, we have already started with the geometrical representation of complex numbers in our previous session, and this will be a continuation of the process. We will try to see a few more geometric conclusions in this session. Before we start that, we will try to recall what we have seen in the previous session. Locus of the given complex numbers. Then we have seen geometric representation of complex numbers, right? These are the two concepts what we have covered in the previous session, right? Now, today, we are going to talk a little more about few more geometric conclusions in complex numbers, and we will try to solve the problems relating these conclusions. Now, children, some important geometric conclusions. Now, before we start with, as we are using Z as the complex number in the conclusions and also in the problem, Z, Z1, Z2, regularly we'll be using these complex numbers, right? So we will first define what are Z1 and Z2. We'll say let Z1 is equal to X1 plus IY1 and Z2 is equal to X2 plus IY2 as two complex numbers. Then you are very familiar with the distance formula in Cartesian form, isn't it? When 2 points are given to you, you know how to find out the distance formula. It is nothing but root of x2 minus x1 whole square plus y2 minus y1 whole square. The same distance formula we do have in complex numbers also. Here we define the distance between the points A and B, which are represented with Z1 and Z2, the two complex numbers, is it will be given by AB is equal to mod of Z1 minus Z2. What are Z1 and Z2? Z1 and Z2 are two complex numbers which are representing the points A and B, children. Okay. Now, in that case, you know how to find out the modulus of given complex number, right? So you will just substitute Z1 is equal to X1 plus IY1 and Z2 is equal to X2 plus YI2. Then you will separate the real part and the imaginary part in both of them, so that you will be getting X1 minus X2 plus I into Y1 minus Y2 in the modulus. Okay. Now, what is modulus? Root of real square of the real part plus square of the imaginary part. So you have it as root of x1 minus x2 whole square plus y1 minus y2 whole square is nothing but the distance formula when 2 points are given to you. Okay. Then the next one, what we are going to see is the section formula. You are very familiar with the section formula also, children. In your class 10th, you have seen what is a section formula, right? If P is a point which is dividing a given line segment in the ratio of M is to N, right? Then you define P is mx2 plus nx1 by m plus n and my2 plus ny1 by m plus n. The similar type of formula we do have in complex numbers. So the section formula, what we define here is, if the point P is represented with a complex number Z, what is this point P doing? It is dividing the line segment AB, okay, in the ratio of M is to N. Ratio is given to you. The point which is dividing the line segment AB is given to you, and it is represented with point P. Then the section formula says Z is equal to mz2 plus nz1 by m plus n. You are already given with what are Z1 and Z2 children. On substitution in the place of Z1 and Z2 and separating the real part and imaginary part, we will be getting mx2 plus nx1 by m plus n plus I into my2 plus ny1 by m plus n. This formula is very much similar to what you have seen in your class 10, but the extra part is the imaginary part. There we have never discussed the real part and imaginary part. Why so? Because both the coordinates are taking the real values. Here one is real value and the other one is imaginary value. And also we always define in complex numbers with the real axis and imaginary axis. Okay, please do both this point in mind, children. Right. The next point what we will see is, if z is equal to a plus ib is a complex number, then what should be its conjugate? Its conjugate should be a minus ib, isn't it? If z is a plus ib, then z bar is equal to a minus ib. Then a complex number and its conjugate, when we consider it, the conjugate always represents the image of the given complex number. Okay, conjugate of a complex number represents image of the given complex number. So, and here in this case, your conjugate is the image of z and it is taken about x-axis. Let us see the diagrammatic representation of this, children. If you take the real part and imaginary real axis and the imaginary axis with the origin as O as we consider, then let us take the 2 points z. Z is the complex number which is represented with a plus ib, and z bar is the complex number. The coordinates, see, you are getting it as a and minus b. Positive real part and negative imaginary part. It comes in the 4th quadrant, right? So if you take OZ, what is OZ? OZ is modulus or the distance from the origin to the point. Whatever OZ you are getting, the same distance will be for OZ bar also. That means when you take modulus of a complex number and the modulus of a conjugate, both will be equal. This point we have already seen. Okay, then if you drop a perpendicular from the point Z onto your real axis, that is equal, and from Z bar also to the real axis, both are same. We have taken the equal length. So we can definitely say this is Z bar is the mirror image of the given complex number Z, and this is about x-axis. Now, the equation mod z minus z1 and mod z minus z2 represents the perpendicular bisector of the line segment AB joining z1 and z2. Two complex numbers are given to you, children. Two complex numbers, they are represented with the points A and B. Okay, so when you join those 2 points, you are getting a line segment. A is represented with Z1 and B is represented with Z2. Now, if I consider a perpendicular bisector, perpendicular, it makes 90 degrees angle. Bisector is a line which divides the given line segment into 2 equal parts, isn't it? So, now if I consider this is a perpendicular, children, and also the bisector. Now, I'm taking a point P on the perpendicular bisector. Now, you are very much familiar with the point. See, when you take a point on the perpendicular bisector, the point will be equidistant from the 2 ends of the given line segment. Okay. So, whatever distance you are getting for from A to P, the same distance you will be getting from P to B. Okay, that's what we are representing here in the modulus. Z minus Z1 is nothing but the distance between A and P, and Z minus Z2 is the distance from P to B. Hope you got that. Then the equation of the straight line joining A Z1 and B Z2 is argument of Z minus Z1 by Z minus Z2 equal to 0 or pi. Now, if you are given with two complex numbers, that is Z1 and Z2, which are taken on a straight line, okay, children, then the join of this will, when you consider, you should get a straight line equation. That straight line equation can be calculated with this formula. Argument is nothing but theta, isn't it? So argument of Z minus Z1 by Z minus Z2 is equal to 0 or pi. That means if the angle what you're taking is 0 or pi, you will get a straight line equation when you calculate Z minus Z1 by Z minus Z2. Now, in general, to prove this, we from where you are getting this Z, you are considering a point, a general point on the straight line. Like how you take y minus y1 is equal to m into x minus x1 in the coordinate planes, what we were discussing in the previous classes. Here we will take P as a general point. Now, the next one, equation of the circle with center C and radius R is mod of Z minus Z naught is equal to R. Now you take a circle, children. Let us consider the center of this circle. We will represent the center with C, and the complex number what I am taking is Z naught. Okay, Z naught will be represented with X naught plus IY naught. And I will take a point on the circumference of the circle. I will call it as P. That P will be represented with the complex number Z. Then if you take the distance between the center and the point, that is nothing but the radius, isn't it? A radius is defined as the distance from the center to any point on the circle, right? That R is nothing but Z minus Z naught. Z minus Z naught is the modulus of Z minus Z naught is nothing but distance between C and P, and that is nothing but your radius. Equation of the circle with Z1, Z2 as ends of the diameter. Okay, when you are given with ends of the diameter, then you can always write a circle equation. That circle equation can be calculated with the formula argument of Z minus Z1 by Z minus Z2 is equal to plus or minus pi by 2. That means when the angle is 90 degrees, okay, when you take Z minus Z naught, Z minus Z1 and divided by Z minus Z2, then you are going to get a circle equation. Or the other condition what you have is, if you take Z minus Z1 by Z minus Z2, if this value happens to be purely imaginary, that means you should not have any real part in that, then in that case also you will be getting a circle equation, right? So argument of Z minus Z1 by Z minus Z2 is equal to plus or minus pi by 2, or Z minus Z1 by Z minus Z2, if it is purely real, then it represents a circle with Z1 as Z2 as ends of the diameter. Now we will see the diagrammatic representation of this, children. Now we will take the 2 points Z1 and Z2 as ends of the diameter, okay, and you take any point on the circle, we will call it as P. Then you just join Z1 to P and Z2 to P. If you can observe carefully, this is the angle what we are taking in the semicircle. Angle in the semicircle, it is 90 degrees, right? So we are taking ends of the diameter and one general point on the circle, right? So when you have such type of information, then equation of the circle can be calculated with the condition what I have mentioned above. Now the next case, the locus of a point Z is a circle if Z minus Z1 by Z minus Z2 taken inside the modulus, if it is equal to some k, where k is not equal to 1, if k is other than 1, any constant value, when you calculate the modulus of z minus z1 by z minus z2, then it always represents a circle. See, these are the points which will be very helpful when you solve multiple choice questions, children. And sometimes if you're solving 2-mark questions also, this will be comfortable. Okay. Now, the equation of the ellipse with foci at Z1 and Z2 is mod of Z minus Z1 plus mod of Z minus Z2 is equal to 2A, where 2A is greater than mod of Z1 minus Z2 and 2A is the length of major axis. Now we will try to see a little description of what is the what do you mean by this foci and also the major axis. Now when you consider an ellipse, children, ellipse will have two axes. One is major axis and one is minor axis. Okay, depending upon how the ellipse is positioned. Now, if I take the position of the ellipse like this, my major axis will be represented with this blue line. Okay, and this major axis, the general equation of an ellipse will be x square by a square plus y square by b square will be equal to 1. And the length of this major axis will be represented with 2a. And we do have minor axis. Minor axis will be exactly perpendicular to this major axis, and that will be represented with 2b. Now, for any ellipse, we will have two foci. That means, see, plural of focus is foci, children. So, S1, one focus I am representing with Z1, and the other one S dash I am taking as the second focus, and I am representing that with the complex number Z2. Okay. Now, we have one property in ellipse. The property says, if you take a point on the ellipse, then SP plus S dash P will be always equal to 2A. This is an important conclusion what we will be seeing in the topic ellipse when we discuss. Okay. So here, now I'm taking a point P on the ellipse. If you join S to P, it gives SP and S dash P. This is what I am mentioning. Now, when you take SP, it is given by mod of Z minus Z1. And if you take S dash P, it will be given by Z minus Z2 modulus, isn't it? So, SP plus SP dash is nothing but 2A. And what is this condition telling you? Now, let me give a little description about this. Now, Z minus Z1 modulus is nothing but the distance between S and S dash. Okay. But what is 2A? 2A is the length of total major axis. Now, major axis in the diagram, if you can observe, the major axis length is more than the distance between Z1 and Z2. Okay. Now, this is one concept what you are going to learn in the ellipse topic, children. So, as of now, I think the description what I have given is suffice. Okay. So, modulus of Z minus Z1 plus mod of Z minus Z2 is equal to 2A, where 2A is greater than mod of Z1 minus Z2. And 2A, we are taking it as length of the major axis. Now, the next one is equation of hyperbola with foci at Z1 and Z2 is mod of Z minus Z1 minus mod of Z minus Z2 is equal to 2A. Okay, where 0 less than 2A less than mod of Z minus Z1. This is the condition what 2A is satisfying. Now, I'll try to explain this by taking the diagram. Your hyperbola will be looking like this. Now, the general equation of the hyperbola will be taken as x square by a square minus y square by b square equal to 1. Okay, this again, when we discuss hyperbola, we'll look into that, children. Now, for hyperbola also, you will have foci, two foci. That means I'm using the word foci because it's more than one. One focus, I'm taking it as S, which is represented with Z1, and the other focus I'm representing with S dash with Z2 as a complex number, which is representing. Now observe this, children. If you take the distance between S and S dash, it is nothing but mod of Z1 minus Z2. Okay. Now just observe the distance. You can clearly see from the picture. Now, what is this 2a? 2a here is the length of the major axis again. Now, the major axis in the hyperbola starts from the vertex here. You just observe the conic what I have on my left hand side. Exactly at the vertex from here to here is 2a. Clearly from the picture, you can say mod of Z1 minus Z2 is bigger value than 2a. And it is not definitely equal to 0. That's the reason why he says the length of major axis, that is 2a, will be lying between the distance between S and S dash and also 0. This is what is the condition telling you. And this condition what we have here says that in hyperbola, SP minus S dash P is equal to 2a. That's the reason why we are taking mod of Z minus Z1 minus mod of Z minus Z2 is equal to 2a. Okay. And for further information, children, we will, you can also revisit this slide or this session after you complete ellipse and hyperbola concepts. Okay. Now here, just to represent that, we are taking a general point on the hyperbola as P. If we calculate SP and S dash P, if you subtract one from the other, then you're going to get the answer as 2a. Now, you are very familiar with collinear points. What are collinear points? If three or more lines, if three or more points, if they lie on the same straight line, we say the points are collinear, isn't it? Now, in complex numbers, if you are given with three complex numbers, Z1, Z2, and Z3, you can say they are collinear if and only if we have certain conditions. The conditions say Z1 in the first row, modulus of, see, we are taking the determinant of all this. What determinant you are taking? Z1, Z1 bar and 1 in the first row, Z2, Z2 bar 1, Z3, Z3 bar 1. If you take this matrix and take the determinant and if it is equal to 0, you can say the given three complex numbers are collinear. Not only that, we have a few more conditions. Now, suppose if you have Z3 minus Z1 and Z divided by Z2 minus Z1 is purely real, right? When you calculate the value of Z3 minus Z1 by Z2 minus Z1, if you are getting the answer as purely real, what do you mean by purely real? You should not have any I term, isn't it? So in that case also we can say the given complex numbers are collinear. And then the next one is argument of Z2 minus Z1 if it is equal to argument of Z3 minus Z1. That means if both the angles are equal, in that case also we can say the points are collinear. And the last condition what we have is if the given three complex numbers are in AP. What is AP? Arithmetic progression. Then we can also say the given complex numbers are collinear points. They are representing collinear points. We will see a few problems, children. Find the equation of the perpendicular bisector of the line segment joining the points 7 plus I, 7 minus 7 plus 7I and 7 minus 7I in the Argand plane. Now, how to solve this? You are given that equation of the perpendicular bisector, equation of the perpendicular bisector, it will be given by mod of Z minus Z1 is equal to mod of Z minus Z2, and you have two values Z1 and Z2 given as 7 plus 7i and 7 minus 7i. We will just substitute in the place of Z1 and Z2 children. Then you have it as mod of x plus iy minus 7 plus 7i is equal to mod of 7 plus x plus iy minus 7 minus 7i. Modulus here says you are taking square root of a real part square plus imaginary part square, isn't it? So first, before doing that, we will try to rearrange the terms, real parts and imaginary parts separately on both sides. Then you will have mod of x minus 7 plus I into y minus 7 is equal to mod of x minus 7 plus I into y plus 7. Then you have it as root of x minus 7 whole square plus y minus 7 whole square is equal to root of x minus 7 whole square plus y plus 7 whole square. Now we'll try to take squaring on both sides, children, so that you will you can cancel the roots on both sides. Then you will have it as x minus 7 whole square plus y minus 7 whole square is equal to x minus 7 whole square plus y plus 7 whole square. Then you, if you can observe the equation carefully, x minus 7 whole square can be cancelled on both sides, isn't it? Then you will be left with y minus 7 whole square is equal to y plus 7 whole square. We will expand that. You will have it as y square minus 14y plus 49 is equal to y square plus 14y plus 49. Then we can cancel y square on both sides, children, and 49 also gets cancelled. Then you are left with minus 14y and plus 14y on either sides of the equality. Then get all the terms to one side. You will have it as minus 14y equal to 0, which is minus 28y equal to 0. That is y equal to 0. What is y equal to 0? It is nothing but equation of x-axis, isn't it? So therefore, the required perpendicular bisector is y equal to 0. Y equal to 0 is representing x-axis. That means x-axis bisects the given line segment. This is the geometric conclusion which we are giving in this problem. Or in fact, he is asking perpendicular bisector, so we are describing it. We'll see another problem. If z is equal to x plus iy and if the point P in the argand plane represents z, then describe geometrically the locus of z satisfying the equations. Under this, we will take the first problem, children. IM stands for imaginary part, isn't it? We were discussing in the previous sessions. So imaginary part of z square is equal to 4 is the condition given to us. We need to simplify this and we need to talk something about its geometrical importance. So you are given that z is equal to x plus iy. We will calculate z square. Z square is equal to x plus iy whole square. Then you have it as x square plus 2x iy plus iy whole square. Okay, we'll expand this. Iy whole square is nothing but I square y square. I square is minus 1. So this value is minus y square, isn't it? So we are writing it as x square minus y square plus I into 2xy. That means we are rearranging the given equation with the real part plus some imaginary part. So we can say imaginary part of z square is equal to imaginary part of x square minus y square plus I into 2xy, which is already given as equal to 4. Now what is imaginary part in this? It is nothing but 2xy, isn't it? That means 2xy is equal to 4 is given to us. Now 2xy is equal to 4 can be simplified as xy is equal to 2. Therefore, the locus xy equal to 2 represents a rectangular hyperbola. Now, I was talking about hyperbola, children, in the previous slides. That is x square by a square minus y square by b square equal to 1. Now, one specific case in hyperbola is rectangular hyperbola. Now, generally, when you talk of rectangular hyperbola, it will have two forms. One form is x square minus y square equal to a square. Okay. Now, x square minus y square equal to a square represents a rectangular hyperbola. If that x square minus y square is equal to a square is rotated through an angle of 45 degrees in clockwise direction, then we will get one equation that is xy is equal to c square. We will see about this in detail when we talk about hyperbola concept. Okay, so this xy equal to c square also represents a rectangular hyperbola. Right, children? So two forms will be there for rectangular hyperbola. One such form is xy is equal to c square. Now, if you observe your locus, what you got, xy is equal to 2. I can always say xy is equal to root 2 whole square. So it is something like c square form only. Now, how that diagram looks like, we'll just see. This is what is the rectangular hyperbola represented with xy is equal to 2. Now, how to get this diagram? You can just go with a graph, take some value for x and y. You can always get this form of this geometrical representation. Right? Now, the next problem. Argument of z minus 1 by z plus 1 is equal to pi by 4. Now, children, z minus 1 by z plus 1, we will try to calculate first. Z is x plus iy already given to us. So, we are just substituting here x plus iy minus 1 by x plus iy plus 1. We will rearrange the terms with real and imaginary parts separated. Then we will have it as x minus 1 plus iy by x plus 1 plus iy. Now, we will try to multiply with its conjugate and divide with its conjugate, isn't it? Why we are doing so? We don't have the given complex number in the form of a plus ib. So first we will try to get it in a plus ib form. When we multiply and divide with the conjugate, we will have it as x minus 1 plus iy into x plus 1 minus iy by x plus 1 whole square minus iy whole square. Then when you expand it, you will have it as x minus 1 into x plus 1 minus x minus 1 into iy plus iy into x plus 1 minus iy into iy divided by x plus 1 whole square plus y square. Okay, children, we will try to expand this. You will, this is nothing but a plus b into a minus b form. So you are getting it as x square minus 1. And this one, when you expand, x into iy is ixy with a minus sign. So minus ixy, minus into minus plus, 1 into iy is iy. Then iy into x is iyx, plus into plus is plus, iy into 1 is iy. Then I square is minus 1. Minus 1 into this minus gives you plus y square divided by x plus 1 whole square plus y square. Now, we'll try to see whether any terms are getting cancelled. Clearly, that xy term with I, they get cancelled, isn't it? So, you are left with x square plus y square minus 1. This comes under real part. I'm separating the denominator also with this plus I into iy plus iy is 2iy. So I is out. So 2y divided by x plus 1 whole square plus y square. Now, argument of z minus 1 by z plus 1 is given as pi by 4. Now, you already know the formula tan theta or theta is equal to tan inverse of y by x, when you take z is equal to x plus iy, isn't it? Now, when you take the value here, z minus, all this is z minus 1 by z plus 1. Now, what is your y in this problem? This whole imaginary part is y and this whole real part is x, according to this formula. So, theta, that is pi by 4, is nothing but tan inverse of this y. That means the imaginary part by the real part, what you have calculated here in this statement. Okay. So you have it as tan inverse of 2y by x plus 1 whole square plus y square divided by x square plus y square minus 1 by x plus 1 whole square plus y square. Now clearly denominators here, they get cancelled. You will be left with, when you take the tan inverse to the other side, it becomes tan pi by 4, right? Then you are left with 2y by x square plus y square minus 1 is equal to tan pi by 4. What is pi by 4? Pi by 4 is 45 degrees. Tan 45 is 1, isn't it? So 2y by x square plus y square minus 1 is equal to 1. Go for cross multiplication. You will have it as 2y is equal to x square plus y square minus 1. Get all the terms to one side, children. Then the locus is representing a circle equation, that is x square plus y square minus 2y minus 1 equal to 0. This is representing a circle equation where the center is taken as 0, 1. Why it is 0? You don't have x term here, isn't it? You have some x square term, y square term, then y term and constant. So you are getting the center as 0, 1 minus g, minus f, and the radius, you are getting it as 2. Then how the diagram looks like? You are getting a circle with the center on y-axis. And the radius is root 2. Hope you got this, children. We'll go with the next problem. If Z3 minus Z1 by Z2 minus Z1 is a real number, then show that the points represented by the complex numbers Z1, Z2, Z3 are collinear. Now, I want you to observe the point given here. Z3 minus Z1 by Z2 minus Z1 is a real number. Imagine, you need to understand this. Imaginary part is 0, isn't it? When it is a real number, imaginary part should be 0. So you are given that Z3 minus Z1 by Z2 minus Z1 is a real number. This implies imaginary part is 0. So we will start substituting the points Z1, Z2, Z3 with x1 plus iy1, x2 plus iy2, and x3 plus iy3. Then when you substitute in the condition given to you, you will get x3 plus iy3 minus x1 plus iy1 by x2 plus iy2 minus x1 plus iy1. Now, when you rearrange the terms, you will get this as x3 minus x1 plus I into y3 minus y1 by x2 minus x1 plus I into y2 minus y1. Okay, since you have I in the denominator, we will multiply and divide with its conjugate. Then you will have it as x3 minus x1 into x2 minus x1 plus I into y3 minus y1 into x2 minus x1, this is the term, minus I into this x3 minus x1 into y2 minus y1 with minus I in front of it. And then I into this I is I square, plus into minus is minus. You have it as y3 minus y1 into y2 minus y1. All this is in the numerator. And in the denominator, it's like a plus b into a minus b, children. So you will have it as x2 minus x1 whole square minus I square into y2 minus y1 whole square. Then we will try to separate the real part and the imaginary part. So the real part is without I, children. So we are getting it as x3 minus x1 into x2 minus x1 plus y3 minus y1 into y2 minus y1 divided by x2 minus x1 whole square plus y2 minus y1 whole square plus the imaginary part. What you're getting is y3 minus y1 into x2 minus x1 minus x3 minus x1 into x2 y2 minus y1 divided by x2 minus x1 whole square plus y2 minus y1 whole square. Now what is the condition given to us? Yeah, the real part is 0. Sorry, the imaginary part is 0. Imaginary part is 0 means the coefficient of I should be 0. That means y3 minus y1 into x2 minus x1 minus x3 minus x1 into y2 minus y1 divided by x2 minus x1 whole square plus y2 minus y1 whole square equal to 0. Okay, cross multiply this, then you will be left with y3 minus y1 into x2 minus x1 minus x3 minus x1 into y2 minus y1 is equal to 0. Okay, now this minus term, we will send it to the other side. You will have it as y3 minus y1 into x2 minus x1 is equal to x3 minus x1 into y2 minus y1. Now, we will rearrange this these terms like this. I can always get this x3 minus x1 as the denominator to the left hand side, and this x2 minus x1 can be sent to the other side. So we will be left with y3 minus y1 by x3 minus x1 is equal to y2 minus y1 by x2 minus x1. So if we consider A represented with x1, y1, B as the point represented with x2, y2, and C as the third point with x3, y3, then which are representing the complex numbers z1, z2, and z3, then I can clearly say this is nothing but slope, children. What is slope of AC? AC is slope of AC is nothing but y3 minus y1 by x3 minus x1. What is the slope of AB? It is y2 minus y1 by x2 minus x1. So slope of AC and slope of AB are equal. Okay. Therefore, the given complex numbers are representing collinear points because A, B, C are the 3 points which are lying on the same straight line. How can I conclude that? Because slopes of AB and AC are equal. Okay, we will see one more problem. Show that the points in the Argand plane represented by the complex numbers -2 plus 7i, -3 by 2 plus 1 by 2i, 4 minus 3i, 7 by 2 into 1 plus I. These are the 4 points given to us. We have to show that they are representing the vertices of a rhombus. Now, before we get into the problem, let us try to talk something about rhombus. What is the speciality of rhombus? Can anyone tell that? Rhombus will have all the sides to be equal. Then what is the difference between the square and the rhombus? Square also has got equal sides, isn't it? The only difference what we can tell about rhombus and a square is, in a square, the diagonals will be equal, children. But in rhombus, the diagonals are not equal. All the sides are equal in a rhombus, but diagonals are not equal. But in a square, all the sides are equal and also the diagonals are equal. So we will start the problem. You are given with the 4 points. Let us represent them with A, B, C and also D, right? They are representing complex numbers in the Argand plane. Then we don't know whether it is rhombus or not. We are just taking a rough diagram of a quadrilateral. Before I tell that it is a rhombus. Let us call it as a quadrilateral with 4 vertices. Okay. A is representing minus 2 comma 7, B is minus 3 by 2 and 1 by 2, C is 4 comma minus 3, and D is 7 by 2 comma 7 by 2. Now we will calculate what is AB square, right? A distance formula. We have seen right in the beginning of today's session. AB square is, you will have it as x2 minus x1 whole square plus y2 minus y1 whole square under root. But since we are taking square, that root is not seen here. So minus 3 by 2 minus of minus plus 2, isn't it? So plus 2 whole square plus half minus 7 whole square. We will simplify this, children. If you take LCM, it is 2. So you'll get minus 3 plus 4, which is nothing but 1 by 2 whole square in the first bracket. And then this is 1 minus 14, which is minus 13 by 2 whole square. 1 by 4 plus 13 whole square is 169. 169 by 4. So you are getting it as 170 by 4. AB square is 170 by 4. Likewise, we will calculate what is BC square. BC square is 4 plus 3 by 2 whole square plus, excuse me, minus 3 minus 1 by 2 whole square. Now, just look at this. You will have it as, if you take LCM and simplify your bracket, the first bracket, it becomes 8 plus 3 by 2, which is 11 by 2 whole square. And here in this bracket, it is minus 6 minus 1, that is minus 7 by 2 whole square. So 11 by 2 whole square plus minus 7 by 2 whole square. 11 whole square is 121. 121 by 4 plus 49 by 4. 121 plus 49, which is nothing but 170 by 4. Now, CD square is nothing but 7 by 2 minus 4 whole square plus 7 by 2 plus 3 whole square. Then 7, first bracket, when you look at 7 minus 8, which is nothing but minus 1 by 2 whole square. And what about this 7 plus 6? That is 13 by 2 whole square. Right? Minus half whole square plus 13 by 2 whole square. This is nothing but 1 by 4 plus 169 by 4, which is nothing but 170 by 4. Now, likewise, we will calculate dA square. dA square is nothing but minus 2 minus 7 whole square plus 7 minus 7 by 2 whole square. Now, what do you have here? Minus 4 minus 7, that is minus 11 by 2 whole square plus 7 minus 7 by 2, which is 14 minus 7, that is 7 by 2 whole square. So you have it as minus 11 by 2 whole square plus 7 by 2 whole square. Minus 11 whole square is 121. So 121 by 4 plus 49 by 4, which gives you 170 by 4. Now, clearly, if you observe all these distances, what we have calculated, we will get it as AB square is equal to BC square. It is also equal to CD square and also equal to DA square. That means all the sides of the quadrilateral are equal. Now, still I am not saying it is a rhombus, children. We didn't confirm yet. Okay. So when the squares of this are equal, we can always say AB equal to BC is equal to CD equal to DA. Okay. Now we'll go for the calculation of length of the diagonals. AC square is equal to 4 plus 2 whole square plus minus 3 minus 7 whole square, which is nothing but this is 6 square 36. This is minus 10 whole square 100. 36 plus 100, which is nothing but 136. Now we will calculate the diagonal BD square. BD square is 7 by 2 plus 3 by 2 whole square plus 7 by 2 minus 1 by 2 whole square. Okay, then you will get in the first bracket as 10 by 2 whole square, and this is 6 by 2 whole square. 10 by 2 whole square plus 6 by 2 whole square. This is 100 by 4 plus 36 by 4. So you will have it as 136 by 4, children. Now, clearly, AC square is not equal to BD square. When AC square is not equal to BD square, AC is not equal to BD. Therefore, the sides are equal, but diagonals are not equal. So we can conclude saying that the complex numbers are representing a rhombus. Okay. Now, one more problem we will look into, children. Show that the complex number Z satisfies Z square plus Z bar square is equal to 2 constitute a hyperbola. This is an important result, I can say. You can take it as a 4-mark question also. Okay. You let us consider Z as x plus iy, children. So when Z is equal to x plus iy, Z bar is equal to x minus iy. Now you are given with the condition that is Z square plus Z bar whole square is equal to 2. Okay, so we will just substitute the values what we know in this equation. So we will have it as Z plus I whole square plus Z minus I whole square equal to 2. We will expand it. So when we expand, you will get it as x square plus 2x iy plus iy whole square plus x square minus 2x iy plus iy whole square is equal to 2. Okay, now we can cancel the terms 2x iy plus 2x iy and minus 2x iy. And what is left with? You have x square plus x square, which is 2x square. And then you have I square y square, which is nothing but minus y square. And here it is minus y square. So it is minus 2y square. So you have it as 2x square minus 2y square equal to 2. I can take 2 common. And when I take 2 common, I'll get 2 into x square minus y square equal to 2. Right? So x square minus y square, I can cancel 2 on both sides. Then you will be left with x square minus y square equal to 1. Now, when I was discussing the previous problems, I said, when you talk of hyperbola, we have a specific condition like rectangular hyperbola. One rectangular hyperbola, what we did in the previous slides is xy is equal to c square. When I was describing that, I said x square minus y square equal to a square also represents a rectangular hyperbola. And if that x square minus y square equal to a square is rotated through an angle of 45 degrees in the clockwise direction and simplify, then you will get an equation xy equal to c square. There in that problem, xy equal to c square we got, so we called it as a rectangular hyperbola. Here, the equation is of the form x square minus y square equal to 1. That is some a square form. Therefore, it is also a hyperbola, or in specific, I can say it is a rectangular hyperbola. Okay, children. So based on today's concepts, I want you to try some questions. You can take a screenshot of this and you can try doing this. The questions what we have discussed today and the practice questions what you can see now in this slide, they are for 4 marks in your IPE exams.
So, madam, completed?
Thank you. Completed, madam.
Yes. So, my dear children, hope you have understood the detailed explanation what madam has given. So, try to practice the questions that are given under practice questions. They are also very important. As madam has said, complex numbers is a major chapter for you people to score 4 marks and 2 marks questions. As such, we are not putting any stress on the examination, but then this chapter you will require it for your future things also. There is one more connecting chapter to complex numbers, which is De Moivre's theorem. that is coming up after this chapter. So try to post doubts so that we will be able to understand how much you people have understood. If it is just one way, it is not in a good way that is going. So if you can please post your questions, it will be of great help for the teachers to get back to you and to make you understand in a better way. So we are hoping to have more doubts for the next session. Thank you so much, madam, and
Thank you,
thank you,
madam.
students. And we are ending this session here.
Thank you.
Yeah, ma'am. Madam Manjari, madam, are you there?
We are on live. Just wait.
Yeah. Are there any doubts, madam? The host, if you can let us know what are the comments. Madam, are there any doubts posted?
Meanwhile, shall I discuss this practice questions, madam?
Yes, madam. Please go ahead.
Yes. Now, third and fourth questions, children, in the practice questions part, you can clearly see that they are in the third question, the 3 points he is asking you to check whether it is representing an equilateral triangle. Okay. So